takes linear programming, which, let's be honest, can feel like a really dry exercise in matrix algebra,
Yeah.
and it turns it into a geometric way of viewing the world.
Yes.
It kind of argues that if you can't see the shape of the problem, you don't really understand the solution.
That is the core philosophy. I mean, Bertsimas and Tsitsiklis state it right in the preface. They say, insight matters most. They aren't trying to turn you into a calculator. They want you to think in, not dimensional space.
To see the shapes.
To visualize the polyhedra. Because once you get the geometry concepts like convexity and vertices and hyperplanes, the algebra just becomes the machinery you use to navigate that space. It's the tool, not the point.
So our mission today is to try and bridge that exact gap. We're going to move from what they call the art of formulation to the geometry of polyhedra. We'll crack open the engine of the simplex method, get a little philosophical with duality, and then finally tackle the complexity of, well, solving the unsolvable.
Sounds like a good plan.
But before we get to the non-dimensional shapes, I think we have to address the elephant in the room.
The word linear.
Exactly. We live in a profoundly nonlinear world. Fluid dynamics is nonlinear. Einstein's gravity is nonlinear. I mean, even my coffee cooling down on the desk here is a nonlinear exponential decay.
Right.
So why is a field that's dedicated entirely to linear optimization, to straight lines and flat planes, why is that considered the bedrock of modern engineering?
It's a totally fair objection, and it's usually the first one a physics major raises when they encounter this stuff.
I can see that.
The answer is really twofold. First, linear is a surprisingly flexible approximation. We have these incredibly sophisticated ways, which I'm sure we'll get into, to model curved, complex realities using piecewise linear functions.
Okay, so we can sort of stitch together straight lines to make a curve.
In a way, yes. But the second, and maybe more important reason, is computational power.
So it's the trade-off between something being perfectly accurate and something being actually solvable.
Right, precisely. Nonlinear optimization is, well, it's dark art. You can get stuck in local minima, the math gets incredibly messy, and solving for even 1,000 variables can take, a century.
Right.
Linear optimization, because of this magical property called convexity, allows us to solve systems with millions of variables and constraints.
Millions.
We trade a tiny bit of fidelity for the ability to scale up massively. And in operations research, things like airline scheduling, supply chains, power grid management scale is everything.
Okay, that makes a lot of sense. So let's start where the book starts. The art of formulation. I love that they call it an art.
Me too.
It implies that translating a messy real-world problem into, XX build B isn't just a deterministic process. It requires some creativity.
It absolutely does.
Yeah.
You're taking a verbal description, something vague, like we need to minimize waste in the factory but keep the workers happy.
Yeah.
And you have to map that to decision variables, an objective function, and a set of constraints.
And the standard form is always something like minimize middles and subject to X gas bag and 6 gas busy.
That's the template for almost everything.
So let's look at the classic diet problem. I feel like it's the hello world of the entire field.
It is. Stigler formulated this way back in the 40s. The setup is simple. You have, say, a $1 different foods you can buy, and there are $1 nutrients you need to consume.
Okay.
You have a nutritional floor. You need at least 2,000 calories, at least 50 grams of protein, and so on. The goal is to minimize the cost of the grocery bill while still meeting those requirements.
So your decision variables, the $60 in the equation, are just the amounts of each food you buy. A pound of chicken, half a liter of milk.
Exactly. And your constraints are those nutritional requirements.
Right. And geometrically, each one of those constraints is it's hyperplane, right? The flat wall.
A flat wall, protein greater than or equal to 50, just slices the entire universe of all possible diets in half. You have to be on the greater than side of that wall.
And when you intersect all of those different nutrient constraints,
you carve out a shape, a feasible region. Any point inside that shape is a diet that keeps you alive.
The optimization part is finding which point in that region costs the least amount of money.
And that's all it is. And while, minimizing a grocery bill seems a little trivial,
the structure is universal. As an engineer, if you're mixing different kinds of cement and sand to make concrete with a certain strength,
you're solving the diet problem. Exactly. Yeah. Making alloys, chemical processing, blending gasoline. It's all the diet problem. You're just mixing inputs to achieve a specific output at minimum cost.
But the book moves on really quickly from the basics into something much grittier. They bring up this case study from Digital Equipment Corporation, DEC, from back in Q4 1988.
I love this example.
It wasn't hypothetical. This was a real production planning nightmare they were facing.
And it's a perfect case study because it introduces what we call logical constraints.
Yeah.
So DEC was building 3 types of computer systems, GP1, GP2, and GP3.
Yeah.
They had hard limits on components like disk drives and memory boards.
Okay, that's standard. A resource allocation problem.
That's standard. But the catch was something they called the production mode.
Right, I remember this. It wasn't just a smooth production function. If they produced more than a certain number of units of a particular computer, the whole manufacturing process itself had to change.
Exactly. They went from what they called constrained mode to unconstrained mode, and that switch changed the resource consumption rates for everything.
So it's an if-then statement.
It's a pure if-then statement. If production is greater than X, then resource usage equals Y. To a computer programmer, that's just an if statement. Easy. But to a linear algebraist, that looks like a total disaster.
Because it's a discontinuity. It's a jump.
It's a jump, and linear algebra hates jumps.
So how do you flatten an if statement into a matrix? How do you make it linear?
You have to get clever. You use integer variables, or more specifically binary variables. You introduce a new variable, let's call it dollars, that can only be 0 or 1.
Okay, a switch.
It's a switch. If you had dollars, use a clever trick with large numbers to enforce one set of constraints. If y is dollars, you enforce the other set. This technically pushes us a little bit into mixed integer programming, but the formulation technique is the key insight.
You're encoding logic gates.
You are literally encoding logic gates into the geometry of the polyhedron. You're building little machines out of inequalities.
That's a great way to put it.
Yeah.
This leads us to the other major tool for handling nonlinearity.
Right.
What the book calls piecewise linear convex functions.
Right.
And they spend a lot of time on what seems like a simple function, the absolute value function, $6.
Which is vital.
Right.
It's absolutely vital because the world is full of these V-shapes. Think about error minimization. We often want to minimize the absolute error, right? The distance from the target, not just the raw difference. But the function isn't linear. It has that sharp corner right at 0.
So standard linear programming, or LP solver, should just choke on it. It shouldn't work.
It should, but it doesn't
Okay.
because of this beautiful little decomposition trick. This is a standard interview question for quant roles, by the way. How do you linearize the absolute value of $6?
So how do you do it?
You split the variable $6 into 2 new non-negative variables, 6 plus x in Calder's dollars, and you add a constraint that says the original $6 must equal $6 plus minus $6.
Okay, let's trace that. If my original $6 is, say, positive 5,
Then you would set 6 plus to 5 and $6 to 5, and $6 is 5.
it works. And if my original $6 is negative 5,
Then you set 6 plus to dollars and 6 to 5. The equation becomes 0 minus 5, which is negative 5.
got it. And they both have to be positive or 0.
That's the key. And here's the magic. The absolute value of $6 becomes simply $6 plus $6. So your objective, minimize $6, becomes minimize $6 plus x subject to that constraint, 6x is x plus x dollars, and the non-negativity of the new variables. And suddenly, that sharp V shape is described by perfectly smooth, perfectly behaved linear algebra.
Wow. That has huge implications for data science, right? Specifically in regression. We're all taught to use least squares,
Right, minimizing the square of the error, the Tel Aviv norm.
which is a nice, smooth calculus problem.
Yeah.
But minimizing the absolute error, the L-Dyer-1 norm.
That's a linear programming problem.
Yeah.
And it's often more robust, actually.
Why is that?
Well, if you have wild outliers in your data, squaring the error makes those outliers just explode. They completely dominate the model and pull the regression line way off.
Is a big number squared is a really, really big number.
Exactly. But using the absolute error, the L-Dyer-1 norm, is much less sensitive to those outliers. It's more forgiving. And because we can formulate $6 in this linear way, we can solve massive regression problems using these incredibly fast and reliable LP solvers.
Okay, now, I want to get to the example that I think trips up the most people when they first read this, but is also the most, I don't know, matrix-style cool. The rocket control problem.
Ah, yes. Optimal control, a classic.
Usually when we think of controlling rockets, we think of differential equations. 5 tuples. Position is the integral of velocity. Velocity is the integral of acceleration. It's this continuous, smooth flow of time.
It is. But computers can't solve for continuous time. They don't do calculus directly. They solve discrete steps.
Little snapshots.
Little snapshots. So what the authors show is how to discretize the system. You create a state vector, let's call it $6, and this vector contains your position and your velocity at a specific time, $2.
Okay.
And you have a control input, $2, which is basically your thruster firing at that moment in time.
And the physics equation looks something like $6 at time plus dollar equals some matrix times $6 at time plus some matrix dollars times your control input, $2 at time.
Correct. That equation just tells you where you'll be in the next second based on where you are now and how much you decide to fire the thrusters.
Now, here's the leap that I think confuses people. A novice thinks, okay, I'll just write a for loop in my code to simulate the rocket step by step.
Right, simulate forward in time.
But in optimization, we don't loop. The book says we stack.
That's a great way to phrase it. We don't loop, we stack.
So explain what that means.
We want to solve for the entire trajectory of the rocket all at once. So we define a single massive vector of variables. Let's call it $6. The first few rows of this vector are the position and velocity at time $2.
Okay.
The next rows are the position and velocity at T2 and T2 all the way to the end of the mission, say, to $1,000.
And you do the same thing for the thruster controls.
You do the same thing for the thrusters. You create one giant variable vector that represents the entire history of the flight from beginning to end.
So the physics equation, the constraint, that matrix dollar in our formulation, isn't just a little 2x2 physics update anymore. It becomes this massive, sparse, block diagonal matrix.
Exactly. It becomes a giant matrix that links the state at time to the state at $10, at $10 plus $10, and so on for the entire flight. You turn a dynamic, evolving process into a single, static, geometric object.
So finding the optimal trajectory isn't like watching a movie that plays out over time.
No, it's finding a single point in a, say, 10,000 dimensional space that satisfies all the physics constraints for every single time step simultaneously. The entire flight path is just one vertex on a very, very high dimensional polyhedron.
That is a perfect segue into section 2 of our dive. The geometry. We keep using this word polyhedron. And to a layperson, that's, a Dungeons and Dragons dive.
D20 or something, yeah.
But to a mathematician, it's the intersection of a finite number of half spaces.
Right, let's break that down. A single linear constraint, like 2 dollars plus 3 belly 10, cuts all of space in half with a flat plane. It's a wall.
Okay.
If you have 100 constraints, you have 100 flat walls. If you manage to enclose a region of space with these walls, the shape that's trapped inside is a polyhedron.
And the single most critical property of this shape, the thing that makes all of linear programming actually work, is convexity.
Convexity is the secret sauce. It's everything. A set or a shape is convex if you can take any 2 points inside the set, draw a straight line between them, and that entire line segment is also fully inside the set.
So a cube is convex. A sphere is convex. A donut is not.
A donut is not. The line between 2 points on opposite sides goes right through the hole in the middle. A crescent moon shape is also not convex.
So why does this matter so much for optimization?
It matters because of the difference between local and global optimality.
Okay.
Imagine you are hiking in a big mountain range, and your goal is to find the absolute lowest valley. In a non-convex world, like a real rugged landscape, you might walk down into a small depression. You look around, you see walls on all sides, and you think, okay, I'm at the lowest point.
But you're not.
But 5 miles away, over a ridge, there's a valley that's 10 times deeper. You've gotten stuck in what we call a local minimum.
But in a convex world...
In a convex world, the shape is like a simple bowl. There's only one bottom. If you walk downhill until you can't go any lower, you are mathematically guaranteed to be at the absolute lowest point in the entire universe of the problem.
There are no hidden valleys.
No hidden valleys. This is why we can solve LPs with millions of variables. We don't have to search the whole space. We just have to find any local stopping point, and we know we're done. It's a huge, huge simplification.
And where is that stopping point? The book introduces this core intuition, the concept of extreme points or vertices. The idea is that the optimal solution is always going to be at a corner.
Right. Think of a cut diamond. If you want to find the point on that diamond that's furthest in a certain direction, say, straight up, it's going to be one of the tips.
It won't be in the middle of one of the flat faces.
Never. The objective function, which is linear, basically acts like gravity. It pulls the solution in a certain direction until it hits a wall. Then it slides along that wall, that face, until it hits an edge. Then it slides along the edge until it gets pinned into a corner.
The book gets pretty rigorous here. It's not just an analogy. They define a vertex algebraically.
They do. They define what's called a basic feasible solution, or a BFS. And the idea is that in a nine-dimensional space, a point is a vertex if it's the unique intersection of non-linearly independent constraint boundaries.
So in 3D space, you need three planes to intersect to define a single point.
Exactly. A corner is just the intersection of boundaries. The algebra and the geometry are describing the exact same thing.
Which leads us directly into section 3, the engine, the algorithm that makes this all work, the simplex method. This is George Danzig's great gift to the world from the 1940s.
It really is. And the simplex method is essentially a corner-hopping algorithm. That's the best way to think about it, since we know the best answer has to be at a vertex.
We don't need to look at the infinite number of points in the interior of the shape.
We don't care about the interior at all. We just need to check the corners.
But there could be billions or trillions of corners. We can't just check them all randomly.
No, absolutely not. That's why simplex is so smart. It's an intelligent search, it stands at one corner, one vertex, and it looks down all the edges that are connected to it.
Okay.
And for each edge, it calculates something called the reduced cost.
And the reduced cost is effectively a derivative, right? It's the slope of the objective function along that edge.
Exactly. It's answering the question, if I take one step along this edge, will my objective function improve? Will my cost go down or my profit go up?
And if the answer is yes for one of the edges,
it moves, it pivots to the adjacent corner at the other end of that edge, and then it just repeats the process. It stands at the new corner and asks the same question again.
And what if it looks around and the answer is no for all available edges?
Then you're done. Thanks to that property of convexity, you know you've arrived. You are at the peak of the mountain or the bottom of the bowl. There is no higher ground to reach.
Okay, let's get into the weeds of the algebra a little bit, because the book really emphasizes the role of the basis matrix, which they call dollars on. This is where the actual computation happens.
Right. So if we have our system of equations written as ax, xeb, the algorithm works by partitioning our variables into two sets. There are the basic variables, which are generally non-zero, and the non-basic variables, which we force to be exactly zero.
And the number of basic variables matches the number of constraints.
Precisely. And the matrix baller, the basis, is the square matrix made up of the columns from dollars that correspond to those basic variables. So the geometry of moving from one corner to a neighbor corresponds algebraically to swapping one column out of the matrix ballers and putting a new one in.
And that's the pivot.
That is the pivot. It's really just a very organized version of Gaussian elimination. At every single step of the simplex method, you're just solving the system of linear equations, 6 Decas-Ballers, B1 B-ball, to find the coordinates of the new corner you've just moved to.
Now, the book warns us about a potential pitfall here called degeneracy. This is a case where the neat connection between the geometry and the algebra gets a little out of sync.
Degeneracy is a fascinating and weird edge case. Geometrically, a standard corner in 3D is defined by the intersection of exactly 3 planes, right?
Right.
But what if, by coincidence, 4 or 5 planes all happen to meet at the exact same point? Think of the very top tip of a pyramid with a square base. That single point is the intersection of 4 different faces.
I see. So the geometric point is the same, but the algebraic representation is overdetermined. You have more than one way to describe it.
You have multiple choices for your basis matrix allers that all correspond to the exact same physical point in space. So the simplex method might try to perform a pivot. It swaps one plane for another in the basis, but geometrically you haven't moved an inch.
You're still at the top of the pyramid.
Still there. And your cost, your objective value, hasn't changed at all.
And this can lead to something called cycling, can't it? Where the algorithm gets stuck in an infinite loop, just shuffling basis columns around, but never actually going anywhere.
It can. It's incredibly rare in practice with real-world problems, but it's fatal in theory. A single problem that cycles would break the proof of the algorithm. That's why the book introduces methods to prevent it, like Bland's rule.
What's that?
It's basically a tie-breaking rule. It says, if you have multiple valid moves that you could make, always choose the one involving the variable with the smallest index number. It sounds completely arbitrary.
Like always turn left in a maze.
Exactly like that. But it's been mathematically proven to guarantee you will eventually break out of the cycle and make progress.
Okay, one more implementation detail the book covers that's really important. It's called phase I. We've been assuming that we just magically start at a valid corner. But if I give you a complex set of 10,000 constraints, just finding any valid corner to start with is a hard problem in itself.
It's the ultimate chicken and egg problem. You need a feasible solution to start optimizing, but finding a feasible solution is an optimization problem.
So what's the fix for that?
You cheat. You temporarily change the problem. You add new artificial variables to your equations.
Okay.
These variables act like slop. They essentially allow you to violate the original constraints at the beginning, but you change your objective function. Your new goal for phase I is to minimize the sum of these artificial variables.
So you're trying to drive the error or the slop to zero.
Exactly. If you can successfully solve this new problem and drive the sum of the artificial variables all the way to zero, it means you have found a combination of your real variables that satisfies all the original constraints.
Yeah.
You've found a valid corner of the original problem.
And that's phase I.
That's phase I. Then you throw away the artificial variables, switch back to your real objective function like maximizing profit, and start phase II from that valid corner you just found.
I love that. We solve a fake problem just to find the starting line for the real problem.
It's very pragmatic.
Okay, section 4. This is the part of the course that I think usually breaks people's brains. Duality.
Duality is, without a doubt, the most profound and elegant concept in the entire book. It asserts that every linear programming problem, which we call the primal problem, has a twin, a mirror image problem called the dual.
So if the primal problem is, say, maximize profit, the dual is minimize the value of my resources. Is that right?
That's a great way to think about it, minimizing the cost of the resources. Let's use the factory example again. You have constraints on your resources, hours of labor, tons of steel. The primal asks, given my resources, how many widgets should I make to get as rich as possible?
Okay, standard problem.
The dual asks a different question. It asks, if I were a different person trying to buy these resources from the factory owner, what are the prices I should assign to 1 hour of labor and 1 ton of steel? The goal is to set the prices just high enough so that the total value of the factor's resources is minimized, but still equals or exceeds the profit you could have made by producing widgets.
And the strong duality theorem says that at the optimum, these two values are not just close, they are identical.
Exactly equal. The maximum profit you can generate from using the resources is precisely equal to the minimum value you would assign to owning the resources. There's zero gap between them. It's a beautiful symmetry.
Okay, let's try to ground this. Why does a plant manager or an engineer actually care about duality?
Sure.
Why does the book spend so much time on these things called shadow prices?
Shadow prices are the killer app of duality theory. They are the answer you get when you solve the dual problem. The solution to the dual gives you a price, a value for every single one of your constraints.
Okay, make that real for me.
Let's go back to the factory. You're the manager. You're
Yeah.
running your production plan, and you find that you are completely maxed out on machine A. You physically cannot make any more widgets because that machine is the bottleneck.
The machine is running 24/7. That constraint is active or binding.
It's binding. Now, your foreman comes to you and says, hey, I found a guy who can run us a similar machine for 1 extra hour, but it's going to cost us $200. Do you take the deal?
Well, without duality, I guess I'd have to change the constraint of my model, increase the machine time by 1 hour, and then rerun the entire massive optimization model from scratch to see if the total profit goes up by more than $200.
Which takes time and computational effort. But if you already solved the dual problem alongside the primal, you just look at your solution. You find the shadow price associated with the machine A constraint. Let's say that shadow price is $300.
What does that number mean?
That number literally means for every 1 extra unit of this resource you can find, your total optimal profit will increase by $300. It's the marginal value of that resource.
So if the rental costs $200 and the value it brings is $300.
You rent it immediately. No question. You make a clear $100 profit on the decision. You don't need to run a new simulation. The dual variable is the sensitivity analysis. It turns your engineering constraints directly into financial metrics.
That is incredibly powerful. It tells you exactly where your bottleneck is and exactly how much it's worth to you to fix it.
And conversely, if a constraint is slack, meaning you have unused capacity, like machine B is only running half the time, its shadow price will be 0.
Because getting more of it is worthless to me.
It's worthless. You already have more than you can use. This relationship is called complementary slackness. A constraint is either binding with a non-zero price, or it's slack with a 0 price.
The book also connects duality to something called Farkas's lemma. This feels a bit more abstract, more for the mathematicians, but they say it's crucial for proving things.
Farkas's lemma is what we call a theorem of the alternative. It's the rigorous foundation for a certificate of infeasibility.
What?
Suppose you hire a consultant to schedule your airline fleet, and they come back to you a week later and say, it's impossible. You can't meet this flight schedule with these planes and crews.
My first question is, do I just trust them? Or do they just fail to find a solution?
Yeah.
Exactly. How do you know for sure it's impossible? You ask for a certificate. Farkas's lemma, and by extension duality, says that if a system of inequalities has no solution, there exists a proof. There's a specific vector, a combination of the constraints, that proves a contradiction. The dual problem finds that proof for you. It's a mathematically rigorous way of saying, here's the fundamental reason why this cannot be done.
That's amazing.
Yeah.
Okay, moving on to our fifth section, network flows. The book dedicates a whole chapter 7, to this. Why treat network problems differently? Isn't a flow problem on a network just another linear program?
It is, absolutely. But it's a very special kind of linear program. It has a very special matrix structure. The constraint matrix for a network flow problem, think of it as water in pipes or data in internet cables, only contains the numbers 1, NACOS 1, and 0. That's it.
And this property is called totally unimodular.
Right. And this special structure gives the problem a superpower.
Which is?
It guarantees that if all the inputs, the capacities on the pipes, for instance, are integers, then the optimal solution will always be integers.
Now this is huge, because usually when you solve the generic LP with the simplex method, it gives you fractional answers. The optimal solution is to build 3.57 bridges, which is, of course, useless information in the real world.
Completely useless. But in network flows, you never get 3.57. You get exactly 3 or exactly 4. This means we can solve what are technically integer programming problems, like the shortest path problem or assignment problems, using the much faster and simpler linear programming machinery. We get integer answers for free.
And the famous Max-Flow min-cut theorem shows up here.
It does, and it's just strong duality in disguise. The maximum flow you can push through a network from a source to a sink is exactly equal to the capacity of the minimum cut, which is the tightest bottleneck of pipes that, if you severed them, would separate the source from the sink.
So again, the geometry, which is the cut, explains the algebra, which is the flow value.
It's the same beautiful concept, just in a network context.
Finally, we have to talk about the complexity wars. Chapter 8, this is where the book shifts from how to do it to how fast can it possibly be done.
This is really the dramatic climax of the 20th century theory of optimization. For decades, from the 40s to the late 70s, simplex was king. It worked incredibly well in practice. But mathematically, it was kind of embarrassing.
Why was it embarrassing? It worked.
Because nobody could prove it was efficient in a theoretical sense. In fact, 2 researchers, Klee and Minty, constructed a very specific twisted geometric shape, a distorted hypercube, where the simplex method would be forced to visit every single vertex of the shape before finding the answer.
Oh, wow.
And if you have a problem with, say, on 5A$ variables, that could be 2 internebular vertices. The universe would end long before the simplex algorithm finished.
So simplex is an exponential time algorithm in the worst case.
Yes. And in the world of theoretical computer science, exponential basically means broken or intractable.
Enter the ellipsoid method. This was 1979 from a Soviet mathematician named Khachiyan.
This was an earthquake in the field. Khachiyan published a proof that you could solve any linear programming problem in polynomial time.
So it's theoretically fast, guaranteed. How does it work? Is it another corner-hopping method?
No, it's totally different from simplex. It's a completely alien approach. It doesn't follow edges at all. It starts by drawing a giant ellipsoid, like a big stretched-out football, that you know contains the entire feasible set.
Okay.
It checks the exact center of that football. If the center isn't a valid solution, it finds a constraint that's being violated, and it uses that constraint to slice the football in half. It throws away the bad half, and then it draws a new, smaller football that perfectly encloses the good half that remains.
So it just keeps shrinking the volume of its search space at a predictable rate.
Exactly. It traps the optimal solution in a smaller and smaller page. It was the first mathematical proof that LP is in the complexity class P, which means it's officially considered efficiently solvable.
And yet, nobody actually uses it in practice.
No, practically nobody. Because while it's theoretically faster in the worst-case scenario, it is practically sluggish on average everyday problems. It involves calculating matrix square roots and requires very high-precision floating point numbers. Simplex, despite its theoretical flaw, is just lightning fast on most real engineering data.
It's the classic story of the tortoise and the hare. But in this case, the hare, which is simplex, only takes a nap once every billion years on a weirdly shaped track.
That's a perfect analogy. But the ellipsoid method gave us something even more valuable than a practical algorithm. It gave us the concept of separation.
The separation oracle. The book makes a big deal of this. This is the key to solving the truly unsolvable problems.
It is. The ellipsoid method showed that you don't actually need to write down all the constraints of a problem to solve it. You just need a subroutine, an oracle, that can take any proposed solution point and do one of two things. Either it says, yes, this point is valid, or it says, no, it's not valid, and here is a cutting plane, a constraint that separates this invalid point from the true feasible set.
And this idea is what unlocks problems like the traveling salesman problem, the TSP.
Yes, exactly. The TSP has what are called subtour elimination constraints. For a trip with 100 cities, the number of these constraints is greater than the number of atoms in the known universe. You literally cannot write down the matrix A dollars. It won't fit.
So you have to use what the book calls cutting plane methods.
You do. You start by solving a relaxed version of the problem with almost none of those constraints. You get a solution, which is usually not a single tour, but a bunch of little loops.
Subtours.
Subtours. You feed the solution to your separation oracle. The oracle looks at it and easily spots a subtour, say a tiny loop between New York, Boston, and DC, and says violation. It then generates just that one constraint that is needed to kill that specific loop. You add that single constraint, that cut, to your problem, and you resolve.
You are building the polyhedron on the fly, only as you need it.
You are defining only the parts of the geometry that actually matter for finding your solution. This technique, cutting planes, is the foundation of how all modern solvers handle massive-scale integer programming, like logistics problems with millions of nodes. It's the true intellectual legacy of the ellipsoid method.
It's beautiful. We started this discussion with mixing simple diet ingredients, and we ended up with an algorithm that literally constructs its own geometry as it goes to solve problems with an exponential number of constraints.
It's a long, long way from y of 4 t plus b to ball.
It really is. So let's wrap this deep dive up. We've gone through formulation, the geometry, the algorithms, the philosophy of duality, and the theory of complexity. If there's one thing a listener should take away from Bertsimas and Tsitsiklis, what should it be?
I think it's their original point. Insight matters most. Don't get lost in the algebra. The matrix operations and the pivots, that's just housekeeping. The real intellectual work is in the formulation and in the interpretation. So when you face a complex decision, ask yourself, what is the shape of my feasible set? Where are the corners? And maybe most importantly, always look at the dual. What is the value of my constraints? If you aren't looking at the shadow prices of your bottlenecks, you aren't really managing. You're just guessing.
And for those of you out there who are dealing with discrete problems, where you can't build half a rocket or send 0.3 data packets, that's a whole other beast. The vertices are still there, but the convexity, that beautiful property that makes everything work, is broken. That is the world of integer programming, and that is a story for another deep dive.
A much, much harder story.
Until then, check out the book. Try to visualize the hyperplanes. Thanks for listening.
See you next time.